There we go. Okay, so now it's recording. So yeah, a few announcements here. No video lecture for later this week because of Gentle Thursday, Friday. Okay, related to credit, no credit. So our department chair said it has to be C or higher. I'm this semester going to give credit for the class as long as you get a C minus and higher. So just to help you out a little bit. So if you get a D plus or D or something or below, you won't get credit, but if you, as long as you get C minus or higher, I'm good for it this semester. Okay, so, and I'm going to do what I can, to curve exams, etc., to really work with you guys. Okay, so that may be an option for you, or based on the curves, etc. If you're doing well, just stick with it and get your letter grade. Okay, get an A in the class, which will look better than a credit. Okay. So related to any of those announcements, any questions? Okay. So yeah, next Alex isn't until April 7th. So you've got some time. You can work ahead and take care of Open Pi period. So if you finish it early, remember you're moved on to Open Pi, so you can take care of anything that you are ready to answer. Okay. Okay. So let's move into the topic of today. And so that is, so yesterday, I guess we were talking about electronic configurations of ions. And in particular, we were looking at, there we go, main group elements. And by main group, I mean these ones. So group 1 and 2, and groups, what is that, 13 through 18. Okay, so that's called the main group. And in those, it's pretty easy to figure out, how many electrons are going to be added or subtracted, or in other words, the configuration of these ions, because they all try to get to the noble gases. And so, for instance, arsenic wants to get to krypton, and so that's why arsenic likes to have that configuration. Okay, so it likes to be a 3 minus, and so then its configuration is really just this. Whoops, not that. I don't know what that is. Okay, is that. Okay, so it's just krypton's configuration. Okay, and then likewise, calcium likes to lose 2 electrons, and so its configuration will be just argon. Okay, and so there are exceptions. Chlorine, for instance, likes to be Cl minus most of the time, which has argon's configuration. But you will find some compounds where chlorine is like a +1 or +3 charge, or these really weird charges that don't make sense based on the noble gas configuration. But those are just exceptions, really. And so most of the time, like 99.5% of the time, these elements in the main group will have these predicted charges based on the noble gas configuration. Okay. All right. So now let's talk about the ones in the middle. So we didn't talk about these guys. So the transition metals. Okay. And so those, as the name implies, so they're transition metals, meaning that they transition between charges or between oxidation states. And so we can't really predict what their preferred charges will be. So remember, in a compound, we have to find out what their charges are by context, right? So in this one, for instance, oxygen is -2, so then that means iron is +2. Okay, so that's why we called this iron 2 oxide. Okay, and so when you have these transition metal ions, what's important to realize is that the s electrons leave first. Okay, so for instance, shown here is the electronic configuration for just the atom. Okay, so this is what we did yesterday. One of the examples we put up yesterday was, I think it was a Chem 101 question where it was, just neutral iron, and it was 4s2, 3d6. Okay, and so to show you that, it's 1, 2, 3, 4s2, 3d, and then we just count over 1, 2, 3, 4, 5, 6. Okay, and so the electrons that lose if you're going to form iron 2 are actually these s electrons. Okay, and so the way to remember it is that since this number is higher, so the principal quantum number is higher, that means the orbital is a little farther from the nucleus, and so that means that they're easier to remove. Okay, and so the configuration then for iron 2 is just 3d6. Okay, and then as soon as you start losing more electrons, now you've already lost the s electrons, now you start removing some from the d. Okay, so an iron 3, such as this, for instance, okay, that's iron 3 plus, that will have a configuration of argon 3d5. Okay. Okay, so does that make sense to everybody? Okay, so here's, let's do maybe a couple examples. So what would the configuration be for nickel plus then? Okay, and the easy way to do it is to start with just the neutral atom. Okay, so what would the configuration be for just neutral nickel? So what noble gas are we going to put?
AR.
Yeah, it's going to be argon. Yeah. Okay. And so it's argon 4s2, 3d what? So you just read across, and so that's going to be 8, right? So 1, 2, 3, 4, 5, 6, 7, 8 for nickel. Okay. And so nickel plus is just going to be
AR4S 3D8.
3d8. Okay, yep. So you're losing the s electrons first. Okay. Okay, nickel 2 would be just argon 3d8. Okay. And then nickel 3, it doesn't form that oxidation state, but it would be, I guess it would be 3d7. Right? Argon 3d7. Okay. All right, so this, if you go on to take more advanced chemistry, you'll find that this one, the nickel plus, is really not the case in compounds. And so if you have coordination compounds, what we call, so for instance, you have a nickel plus that's surrounded by waters or anything else, you'll find that these configurations are, this one in particular is really not accurate. Okay, but for this class, we'll just consider it that that's the way it is. Okay, so these are kind of like isolated neutral ions. Okay, sort of just in space. Okay, and so you're losing the s electrons first, followed by the d's. Okay. All right. So now looking at, so starting to talk about some periodic trends. So this is really small. Let's see if I can blow it up. There we go. Okay, so As far as sizes, okay, we already looked at one periodic trend that as you go down a group, atomic size increases, okay, and we saw that because you have increasing orbital size. For instance, for dimensions, a 1s is smaller than 2s, is smaller than 3s, etc. Okay. And so we see that trend here. So these blue lines, or boxes, are showing that trend. So we're going down the group 1, okay, and they're going up in size. So this is radius in picometers, okay? And you'll notice the same trend with ions, actually, okay? So it's the same thing with the positive ions, but you'll notice that the ions, if they're positively charged, so cations, they will always be smaller than their corresponding neutral atoms, okay? And so the reason for that is you're just taking away electrons from it, okay? And so the dimensions, the radius or the diameter of an atom really correspond to, the electron density around a positive nucleus, right? And so if we're taking electrons away, then this radius or diameter shrinks, okay? Okay, so positive ions, so cation size, will always be less than the neutral atoms. Okay, and so then looking at the flip side of that, I guess this is still just the positive ions. So again, you'll see that trend with now we're pulling 2 electrons away, and you see a dramatic decrease. So the more electrons you pull away, the greater is that difference, okay, versus these ones, they decreased, but not as dramatic. Okay, I guess lithium did, because it's small to begin with. And so, when you pull an electron away from lithium, you get helium, which is really small, okay? But if we look at the next group, like beryllium, now it's, even more significant, okay? So I guess this trend is more substantial as more electrons are removed. Okay, so for instance, aluminum to aluminum 3 plus is going to be a huge difference in ionic radius. Okay, so relative to this, the neutral atom. Okay. Okay, and so if you had to guess, I don't know if I have it on the next slide even, but if you had to guess, this is now cations. What do you think happens with anions? What do you think? Which is going to be bigger?
Will anions get bigger because the radius is larger?
Yeah, so anions will be greater. Okay, so for instance, let's look at Cl minus versus Cl. Okay, so the reason for this is because you are adding electrons. So kind of just the opposite for cations, that the more electrons you add, they'll take up space in these orbitals, and so that forces the radius or diameter of the atom to be larger. Okay, so, and I do have, okay. All right. So, and every time you add more electrons, you're getting more electron-electron repulsion, okay, which causes this diameter or radius to increase. Okay, so again, as you go down a group, you're seeing that increase even with the neutral and with the ions, but you're seeing greater increases in the radius as you add electrons. Okay, and this will be more dramatic as you add more electrons. So, for instance, N3 minus is going to be huge relative to just neutral N. Okay. All right, so that's the first periodic trend. The next periodic trend is ionization energy. And the definition for this, I guess, hydrogen is shown there, is really this. So how much energy, and this by definition, they're all in the gas phase. So it's always in the gaseous state is how you define ionization energy. And so it's how much energy does it take to remove an electron from a neutral atom, or I guess that's the first ionization energy is from a neutral atom. But you could talk about even, so this would be ionization energy 1. You could have ionization energy 2, where you're removing an electron from this, which it's not going to happen, but okay, I'll put an exclamation point because it really doesn't make sense for hydrogen, but you can talk about, IE2 or IE3, where you're removing sequential electrons, okay? Like, for instance, one that actually makes sense is aluminum, right? So you can say this one will require a certain amount of energy, and then IE2 is this one, and then IE3 is where we remove through the third electron, okay? And each of these will require energy. It actually requires more energy, so the ionization energy 3 is going to be more than 2, and it's going to be more than 1. Whoops, 1, okay? And so the reason for that is because you're trying to pull an electron from something that has a positive charge. So you've got this kind of mutual attraction, opposite charges attract, right? And so you're trying to pull an electron, something negatively charged, from a positive ion. And so that's going to take more energy than in this case, okay, the very first ionization energy, you're pulling an electron away from something that's neutral. Okay, so it doesn't take as much energy. Okay, and these numbers are pretty significant. So for instance, for hydrogen, it's 1,300 kilojoules of energy is required to remove an electron from a neutral hydrogen atom. Okay, and so here is the trend. And what's interesting is that you will notice that the maximum energy is for the noble gas. So these are all the different periods, okay? And so you'll notice that the lowest energy is for the group 1s, okay? So this is saying that it is easiest to remove an electron from the group 1, okay? And so a low ionization energy means it's easier, it doesn't take as much energy, in other words, to kick off an electron, okay? So it's easiest to remove from the group 1, and then it gets harder and harder to remove an electron, and the hardest to remove an electron from the noble gases, okay? And that makes sense, right? Because these are so stable, they don't want to lose any electrons. They don't want to gain, they don't want to lose. And so the highest ionization energy will be for all the noble gases of whatever period you're looking at. Okay? And then you'll notice that, it goes up as you move left to right in a period, but you've got a couple of anomalous behaviors. So you've got sort of these cases where it's harder, but then it becomes easier, and then it's harder, easier, and then harder. Okay, so let's look at why you have these situations here. Okay, so this, for instance, so if we look at this second period, you'll see that it is harder to remove an electron from beryllium than it is lithium. Okay, and let's look at that. So lithium's configuration is just, if we have this, okay, so that's the configuration for lithium. Lithium plus is just that, right? So we have loss an electron, and so this is the same thing as helium, okay? Or I guess in brackets there, okay? And so very, very stable, okay? Versus beryllium is that, okay? And so beryllium plus would be that and that. Okay, again, you're losing one electron. Okay, and so the reason why this is harder to do, okay, is because it's actually pretty stable here. Okay, so it has, full, all of its orbitals, so the 1s and the 2s are filled. Okay, and so for it to lose an electron, it has to give up its fully filled orbitals. So remember when we were talking electronic configurations, I said that if something has fully filled or half-filled orbitals, it's really stable. Okay, and so this was pretty stable to begin with, and so it's going to something that is not as preferred. Okay, if you go beryllium 2 plus, then you've got helium's configuration, and then it's quite stable. Okay, but we're talking here just kind of removing an electron. The general trend, by the way, of why, forgetting about these little kinks here, but why it is becoming harder to remove electrons as you go left to right. Okay, across a period, it's harder to remove electrons. It has to do with the effective nuclear charge of those electrons. Okay, so as you move left to right, you are adding more electrons to the shell, right? And so because of that, these electrons are experiencing more nuclear charge, okay? So they are being sucked into the nucleus a little bit more. And so we saw that, remember, as you go left to right, the atomic size decreased. Okay, so for instance, lithium may look like that, then beryllium, and then moving over there was like boron, carbon, okay, and it's getting smaller and smaller as you go left to right. Okay, so as you'd imagine, as you're getting smaller, that means the electrons are closer to the nucleus, so they're harder to remove. Okay, so that's the general trend here. Okay, but now let's look between beryllium and boron. So why it's easier to remove an electron from boron than it is beryllium. Okay, so this is the first anomaly. So why is it easier to ionize boron than beryllium? Okay, so let's look at boron. So that's 1s, 2s, and the 2p. Okay, so this is boron. And so the reason for this is because boron actually prefers to be ionized, because if it loses this electron, it's back to a pretty stable configuration, right? So we said that boron was pretty stable because all of its orbitals were filled. Okay, and so this gets you to a configuration where all of your orbitals are filled, and so it doesn't take as much energy to do that. Okay, so that's why boron is a little bit easier to ionize. Okay, and then as we move up, we'll see this trend again between nitrogen and oxygen. So let me do that. We'll forget about the 1s because it's really not involved in bonding here. So we'll talk 2s and a 2p for these. Okay, so nitrogen has nitrogen is 3, right? That, and then oxygen 4. Okay, so these are the configurations for just the neutral atoms, okay? And so does anybody, looking at these configurations, does anybody have a reason why this is easier to ionize? So it's easier to remove an electron.
Because half-filled subshells are like more stable.
Yeah, exactly. Yeah, so so fully filled kind of applied for the boron versus beryllium case, and half filled are also very stable. So if you kick off this one to become O plus, for instance, then that means you've got a half filled P shell, right? Okay, so it's more stable. Okay. So does everybody see that, those trends really? And you'll see that in the other groups too. Some it's not as dramatic. I mean, it has to do with the size of the orbitals in that case. Magnesium to aluminum is pretty dramatic, but then the phosphorus sulfur is not. But yeah, you'll see kind of those anomalies across the different periods. Okay, this is probably the most pronounced in the group or the period 2. Okay, but the general trend is as you go left to right, it is becoming harder to remove electrons. Okay. All right, so you can look at these different ionization energies, and this is a common question on exams, so hint, hint for your next midterm exam, that you'll see, for instance, aluminum, you'll notice, like I said before, that, as you remove electrons, the ionization energy will go up. Okay, so aluminum, to remove that first electron, is 578 kilojoules. Then it goes to 1800, then 2700. Okay, but then it goes to a value that's just crazy high. Okay, and so this is saying, if it goes from 2700, it takes almost 12,000 kilojoules to remove that fourth electron. And so it's saying that, good luck ever trying to remove 4 electrons from aluminum. Okay, and we know that that is the case because aluminum 3 plus is which noble gas? Argon, right? It's argon's configuration. Okay, so nice and stable. Okay, but aluminum 4 plus doesn't really get you anywhere, right? If you remove 4 electrons from aluminum, you get to, where are we? Or no, aluminum 3 plus is neon's configuration. Whoops. Okay, it gets you to fluorine's configuration, so that's not, much more stable. Okay, and so so looking at just these different trends, you can find out, how many electrons something likes to lose. Okay, and a common question is to give you an ion, like it would just say, X. It'll give you some element X, and it'll give you different values for its ionization energy. So for instance, 738, 1451, and 7700. Okay, and so it'll ask you, what is its most stable oxidation state or its charge? And so you would look at this and say, okay, it's increasing, and then it increases big time. So this would be, that. Okay, and so that would be in a group 2, for instance, so magnesium 2. Okay, so does everybody kind of see that? So for this sodium, you go from 500 to 4500. Okay, so that's saying it'll only really want to lose 1 electron. Okay, silicon here, it's increasing. but not so dramatic. It's increasing maybe by 1,500, 1,000, and then 15 or 10,000 going here. So the group 4s, can lose kind of a maximum of 4 electrons, realistically. Okay. All right. Does that kind of make sense? Hopefully. Okay. All right. So that's ionization energy. Okay. How much energy does it take to remove an electron? Electron affinity is just the opposite. So it's how much energy is released when an electron is added. Okay, and this is kind of weird with the units that we have here. So the more negative it is, that means that it is releasing more energy, and that means it's more stable or more preferred. Okay, and so here, the trends, so in electron affinity, I guess I should write it out. Okay, electron affinity, notice that the lowest electron affinity is the group 18s. Okay, they'll have values of 0. Okay, and so the reason for that is because, again, they're already stable. They don't want to add any electrons, and they don't want to remove any. Okay, and then you'll see the trend is really not so clear. It's really not as perfect, if you will, as ionization energy. But you do notice that it is going up as you move left to right. So it is increasing negative values as you go left to right. So sort of a general trend. Okay, so that means, so therefore it is becoming more likely to add electrons as you go left to right. Okay, and we know that that's the case, right? So as you go left to right in the periodic table, all these are electropositive, which means they'll want to lose electrons. And then when we start to get here, they now will add electrons to try to go to the noble gas configuration. Okay, so you start to see the trend kind of make sense as you get closer to the halogens. Okay, so you'll notice, these ones are going up pretty linear, similar trend to ionization energy maybe. But the ones that are always at the highest now, okay, are the halogens. Will have the most negative electron affinity values. Okay, which means that they are most preferred to add electrons. Okay, and we know that's the case, right? Because F is almost always F minus in compounds, and same with Cl and Bri. Okay, and so so that's the trend with electron affinity. Okay, so the more preferred it is to add electrons, the more negative its value will be. Okay, and that corresponds to energy being released when this happens. Okay, so ionization energy requires energy. Okay, or so IE requires energy. In other words, it's endothermic. We're going to talk energy a little bit later. And electron affinity releases energy. In other words, it's exothermic. Okay, to kind of throw out a couple terms here. Okay. So the octet rule is something we're going to talk a lot about in the next chapter when we talk bonding. And it's where main group elements, and we're talking here, again, groups 1 and 2 and 13 through 18. If you count across those, you have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's where the octet rule comes from. is that everything likes to have their orbitals filled, like to have Neon's configuration, and so that would correspond to 8 electrons. Okay? And so when we talk about bonding in compounds, we're going to see that main group elements try to have 8 electrons surrounding them at all times. Okay? And there will be exceptions, as there always are, but there'll be a lot where it absolutely has to have 8 electrons around it when you have compounds. Okay? And so, so some general trends: metals tend to have a low ionization energy and a low electron affinity. Okay? And so that means that a low ionization energy means it doesn't take very much energy to kick off an electron. Okay, so think lithium, for instance. It wants to go to lithium plus really easily. And electron affinity, it really doesn't want to add any electrons. Okay, versus nonmetals, it's really hard to remove electrons from them. So they're going to have a high ionization energy and a high electron affinity, which means that they want to add electrons instead of remove. Okay. Okay. So before I forget, let's go through some of these Chem 101s. So give you some extra credit here. Okay. So trends 1. So there we go. Okay. So valence electrons in which of the following atoms experience the greatest effective nuclear charge? And by valence electrons, I am talking, and what are your options here? Okay, effective nuclear charge, yeah. So valence electrons are the electrons that are farthest from the nucleus. And so, for instance, if we have, I don't know, like nitrogen. Okay, we have this, then that, and then this. Right? 1, 2, yeah, 5. Okay. And so we would say the valence electrons would be in the n equals 2 orbital. Okay, this would be the core electrons. And so we really don't care about those as far as bonding. We only care about these valence electrons. Okay, so we would say that nitrogen has 5 valence electrons, for instance. Okay, and so this question is valence electrons in which would experience the greatest effective nuclear charge. Okay. Yeah, and so, yeah, you're right. So as you move left to right across a periodic table, you're adding more electrons, which means they are experiencing more positive pull from the nucleus. So, yeah, so argon, or the noble gas. Yeah. Okay. Right, so that's trends 1. Trends 2. So effective nuclear charge, just kind of its definition here. So that one's hidden. Okay, so just the, there we go. So is it just the number of protons, or is it nuclear charge minus the charge shielded? Okay. Or something else? Oops. This computer is so slow. Okay. Let me go back. Trends 2. Okay, there we go. Okay, so yeah, so effective nuclear charge is equal to its full nuclear charge minus some shielding factor. Okay, and that corresponds to, electron-electron repulsions. Okay, so that's what kind of shields the valence electrons from experiencing that full nuclear charge. Okay, so that's why it's called effective nuclear charge. Okay. So now trends 3. How many core electrons does an atom of beryllium contain? Okay, yep. So you have 2 valence electrons and 2 core electrons. Yeah. Okay. So by the way, the easy way to count how many valence electrons something has is, again, we forget about these guys, so the transition metals, and we just look at the main group. And so whatever group it's in, 1, 2, 3, 4, 5, 6, 7, 8, that's how many valence electrons it has. So for instance, oxygen will have 1, 2, 3, 4, 5, 6 valence electrons. Fluorine will have 7. Neon will have 8. Okay, and so that's why some periodic tables, they've got the Roman numerals with them. So let me just pull one up here. Periodic table. That one doesn't, but I'm sure you've seen it. But just search. Okay, images. I think this one, yeah. Okay, this, if it ever pulls up, okay. So this, for instance, is blurry, but you can see like this is 3A, 4A, 5A. The Roman numerals here really tell how many valence electrons you have. Okay, so 5A, that means 5 for this group. 4A is 4. Okay, so it's very convenient when we go to the next chapter where we want to count how many valence electrons all the different atoms in the compound have. Just look at its group and just count from there. Okay. All right. So that was 3, I think, or was that 4? Okay, so trends 4. Which of the following atoms has 5 valence electrons? Okay, so let me put up the periodic table. Okay, so you're just looking at which one is in group 1, 2, I guess then it's 13, 14, 15, or 5A. Okay, and so it's in this group here. Okay, so that would be nitrogen. Okay, so carbon would have 4 valence electrons. Okay. All right, trends 5. Okay. Which of the following transition metals would be expected to have the smallest atomic radius? Okay, this one, yeah. There we go. Oh. Okay, you didn't see the answer. Okay, so it's yttrium, zirconium. So these are your possibilities. Niobium. So we've got yttrium, zirconium, niobium, technetium, or ruthenium. Okay, so they're really in the same period. Okay, and so what's the trend as you move left to right in a period? You are decreasing the size due to the effective nuclear charge, right? So this would be ruthenium. Okay, so that's a close one here, but Ruthenium is farthest to the right, and so that will be the smallest radius. Okay. There we go. So everybody's updating their answers. Okay. All right, then trend 6. Okay. In each pair, choose the atom that has the highest first ionization energy. Okay, so this means what is hardest to remove electrons. So aluminum or silicon. Okay. Okay, this one's close too. So aluminum versus silicon, so we're looking here. Okay, so as you go left to right in the periodic table, remember that that ionization energy was going up. Yeah, so you're right. So silicon would have the highest ionization energy. In other words, it's harder to remove electrons from silicon than it is aluminum. Okay. The next one, magnesium or sulfur. Okay, that one. So again, it's in the same period. Yeah, and it would be sulfur, okay, because again, you're moving left to right. So that's hardest to remove electrons. Strontium or oxygen. Okay. Yeah, so most people are picking oxygen, so that is correct. Yeah, so strontium's going to have a very low ionization energy because as you go left to right, it's going to be lower, and as you go down a group too. So as you go down a group, the ionization energy will decrease. Okay, and that means it's easier to remove electrons. So it's easier to remove electrons from larger orbitals. Okay. All right, so that is strontium versus oxygen, and then the last one is potassium or rubidium. So this versus that. Okay, and so again, as you go down a group, it's now easier to remove electrons. So potassium would have the highest one there. Okay. All right, so I think we have, actually, yeah, you don't have to run to another class right now. So let's do this last question on here. Okay, trend 7. There we go. Okay, so in each pair, choose the atom which is larger. Okay, so antimony versus bismuth. Okay, so yep, as you go down a group, it's getting bigger. So bismuth is bigger. Yep. Strontium or tellurium. So strontium's here. Tellurium is way over here. Okay, so tellurium will be smaller. Okay, because you're going left to right. Okay, so yep, strontium's bigger. And then chromium versus chromium-3. Okay, that one, remember that the neutral atom is always larger than its ion. Okay, so it's cation, yeah. So that's correct. And then the last one, selenium-2 versus 2- or tellurium-2-. Okay, and so we're here. And so, yep, so it's the same trend for ions. As you go down a group, the ions get bigger as well. So tellurium-2 is going to be bigger. Okay, so that is it. I guess let me know if you have any questions before we sign off. Does anybody have anything? If not, have a great weekend. Enjoy your gentle Thursday and Friday.